Alright, welcome back to the logic slides. Let's keep on trucking. We have a few more things to get through, I think, today and then next time. Alright, so here is where we stopped. We're learning about predicates, which are not yet propositions, but if you are to apply them to some variables in their domain, then it becomes a true or false statement. Like P of Lawton and cats becomes a true or false statement. It becomes a true statement, right? Things like that. So let's use those in things called quantifiers. Okay, so now that we've got our predicates, it would be nice to be able to talk about a lot of things at once, a lot of values of those variables at once, right? We like to say things like P of x, it's true for every x, no matter what x is. Or, I guess I got ahead of myself. P of x is true for every x, P of x is true for what, no matter what x is. P of x is true for all x. Okay, so there's going to be a quantifier called for all, and we're going to introduce that right now. So we're going to use the symbol upside down A to mean for all. So whenever you see this symbol for all, you read it like that. Okay? So for example, let's say that P of x, let's define that to be Lawton loves x, and the domain of P is all the cats in the universe, then the following statement is true for all x, P of x. Okay? That's something that you can claim to be true, and it becomes a proposition at that point, right? It's something that can be proven to be true or false. And of course, I love every cat, therefore it's true. Does that make sense? So x is allowed to range over every cat. It's like x gets a chance at being my cat, it gets a chance at being every cat in this picture, etc., etc. Okay? One thing that's important about these things called quantifiers, and for all is a quantifier, is that they introduce variables. So for example, I can say for all y, and then I can start using y here. Y can appear after I've introduced it with the quantifier. Y can appear here. Okay? That's the idea. It introduces a new variable, and you can use it from then on. So instead of saying for all x, P of x is true, I could have said for all y, P of y is true, and that would have meant the same thing. For all x, or for all z, P of z is true as well. Okay? So the variable name doesn't matter as long as you're consistent. It's just saying, all right, I am going to range over every possible value, call it y. I'm going to claim that P of y is true for every one of those things. Okay? That's the universal quantifier. For all x, P of x. Okay? On the flip side of that, there's something called the existential quantifier, which does not make as big of a commitment to proving that everything is true as the universal quantifier. All right, so sometimes we don't want to commit to everything. We'd like to just say that P of x, this predicate, it's true sometimes for at least one value of this variable x. Okay? An alternate way to say that is there exists an x such that P of x is true. And so instead of upside down A, we have, well, A flipped 180 degrees, we have E flipped 180 degrees, and that is going to correspond to the word there exists, that phrase. Okay, so example of there exists. So let's define P of x to be Lawton owns an x, and the domain of P is all cars. I only have one car, so it's not true that for all x, P of x, I don't own every car in the world, but I do own one, at least one, so there exists an x such that P of x is true. Do you see how that makes sense? So there is at least one car, and I own it, okay? X gets to be that car. We're not talking about it specifically, it gets to kind of pick it out of the universe of cars. So I own one car, not every single car, okay? So again, that upside down E, there exists, it introduces a variable. And you can use that forever. So there exists a z such that, and then we're talking about z in here. It introduces a variable. Z gets to range over the domain of some predicate. Z can appear here. And this will make a lot more sense once we start giving a bunch more examples. Don't worry. But it introduces a variable, and you can use it forever. So this is equivalent, therefore, to this. There exists a y such that P of y is true. As long as you're consistent, it's all the same. There exists a z such that P of z is true. Those are all saying that there exists a car such that Lawton owns that car. It's just the variable is a way to specify the one we're talking about. All right? That's the idea. As long as you're consistent, as long as these match, it's always the same. Okay? So that's the existential quantifier. And so now, let's get some practice with these. All right? So here are some predicates, P and Q. And the domain of these predicates, they each have one parameter, kind of. The domain of these predicates is the students in this class. All right? So P of X is, let's define that to be X was born in September. Okay, so it's true for some people, false for others. And then Q of X is at least 20 years old. All right? So try both of these. Do you think it's true that for all of X, P of X? Is that a true statement? For every X, P of X is true? And then how about this one? There exists a Z such that not Q of Z is true. So another way to say that is there exists a Z such that Q of Z is false. Okay? So think about those, and then I'll come back and do them. All right. So do you think that it's true that for all X, P of X is true? How would you translate this to English? That's something you have to get good at. So if this is true, right, for all X, for all students in the class, P of X is true for them. So every student in the class, therefore, we're claiming was born in September. Definitely not true, right? That's what it's saying, though. It's claiming everybody in the class, everybody was born in September. I'd be very surprised to learn that that was true. Okay? I really doubt that it's true, so I'm pretty sure it's false. And then this one, it's got a not in there, so it might be a little bit more difficult to think about, but let's walk through it. So there exists a Z, so there exists a student in the class, such that not Q of Z is true for that student. All right? So there exists a student such that they are not, this is not true about them. They are not at least 20 years old. Okay? Does that make sense? So there exists a student, this is claiming, there exists a student such that that student is not at least 20 years old. So they're less than 20. They're younger than 20. So there's, do you see how that's what this is claiming? There's a student in the class who is under 20. And I'm pretty sure that's true. Yeah? So that is how you can pick apart those statements. Hopefully you got close, if not perfect, but keep on trying them. It'll start making sense. Okay? Here's another question for you. So here is, let's pretend we have a predicate, P and Q, two predicates, and their domain is these three things. Like, you just check, hey, is P true for A? You can write it down. Is it true for B? No. Is it true for C? Yes. So you can just write down the predicates in the truth table form if the things that they quantify over are, or the things that their domain ranges over is finite. You can just write it in a table like a truth table. So this is the table showing the value of the predicates for each of the elements in the domain. So you can just look at all of them and determine these. Is it true that for all X, not P of X is true? And is it true that there exists a Y such that not Q of Y is true? Okay, so think about what that means, and then I'll come back and do them both for you. Okay? So, is it true that for all X, not P of X is true? So for everybody in the domain, A, B, and C, try P on them, it better be false, right? That's what not is claiming. It's not true that for all A, B, and C, not P of X is true, right? Because, well, it's true for B, because that one's false. So not P of X is true when X is B, but when it's A and C, it's true. Do you see how that's not working out? Okay? That is not the right idea. So this is, for example, this is the value of P of A. P of A is equal to true. Q of B is equal to true. All right, so sometimes P of X is false, yes, but sometimes it's true, and so it's not true that it's always false. This is claiming that it's always false, okay? And if this is confusing to you, I want to let you in on a little secret. There's a secret about there exists and for all key idea. If you stare at the examples and the definition long enough, this will make sense to you. When you have a for all, it's just a bunch of ands. bunch of ands. And there exists just a bunch, there exists is just a bunch of ors. Let me show you how that makes sense. So really, is it true that for all x, p of x is true? Well, that's, or for all x not p of x is true. Just try everybody in the domain. It's claiming that, like, all right, x gets a chance of being everybody, right? So it's claiming that not p of a is true, and not p of b is true, and not p of c is true. You see how I'm translating that? And if you just look through these, like, sure, this one's true, but the rest of these are false. So this whole thing is equivalent to false. It's not true. This statement is not true. Does it make a little more sense when I think about it that way? So likewise, you can transform this into a bunch of ors. Like, is there a y? Does there exist a y such that not q of y is true? Well, it could have been a, right? Y could have been a. Maybe it's true that not q of a is true. But I just need one, right? So let's try them all. Or maybe b was the answer. Maybe b was the one that made this whole proof go through and make it true. Maybe it's not q of b that's true. Or maybe it's not q of c is true. You see that? And so it's just one. We're just picking out one. There exists some y such that not q of y is true. So it could have been anybody. Just OR them together, and the result is that. All right? And so this is a true statement because not q of c down there. That's true, right? This is true. I don't know how I want to say this. This is equivalent to true because not q of c is a true statement, right? See, it's false there. So again, read the book, go through these examples, but hopefully it's making slightly more sense now. These quantifiers do take a little while to sink in, though. All right? Because you have a bunch of ands and a bunch of ors secretly, De Morgan's laws make sense for quantified statements with for alls and there exists. So you can push a negation inside of a for all or inside of a there exists. So, for example, let's think about what this one should transform into. How can we push this negation inside of the for all? So how would you translate this to English first? You'd say something like, all right, it's not true that for all x, p of x. All right? So if you think about that long enough, it's just saying that, all right, if it's not true for all of them, then there must be somebody that's ruining the party, right? There must be some element of that domain where p of x is not true. See that? So therefore, the negation of that thing, if you push it in, it becomes there exists an x such that not p of x is true. So that's where the negation goes. It goes on the inside thing next to the predicate, and the for all gets flipped to a there exists. Because secretly, it's a bunch of ands getting flipped to a bunch of ors. It makes sense. That's really just the normal De Morgan's rule. Okay? So that's how you negate a for all. It becomes a there exists, and you negate the inside. And the flip side is true for negating a there exists. It becomes a for all, and then you negate the inside. Let's discover that. So how would you negate a there exists quantified statement? So first of all, translate this to English. It's saying it's not true. It's not true that there exists an x such that q of x is true. So if you can't find an x for which q of x is true, then it must be the case, right? It's not true that there exists an x such that q of x is true. If you can't find one, that means they must all be false. None of them work, right? Q of x must be false for every element of the domain. Otherwise, you would have been able to find somebody for which it was true. So that means pushing the negation inside, the there exists becomes a for all. For all x, it must be the case that not q of x is true. You see that? That's where the negation goes. All right, so if you think about it, if you just translate it to English, sometimes this all works out and it makes sense. Okay? So please yell at me, ask me questions about this stuff. It is a bit of a complicated topic. Let's now move to proving things, because you can formulate these statements all day long. We've talked about how to prove them when like the domain is very small. Let's get a bit more general now, because we want to be able to prove these things, true or false. All right? So I guess my first hint to you is proving for all and there exists when you're thinking about how to prove them true or false, statements that include them, it's kind of like you're fighting, okay? So it's weird, but I promise this will make sense if you think about it. When you have a for all, I want you to imagine like your worst enemy is the one trying to get your proof to be false, right? You're trying so hard to make it work, but your worst enemy is trying to pick values for the variable that the for all is quantifying over to make your day go horribly, trying to make that predicate false, right? Your job is to prove that, no, it works for all of them, right? So you get to imagine that your worst enemy is picking the worst possible option, and you have to counter it, okay? So to prove for all of x, p of x, you have to prove that p of x is true for everybody, including the most difficult value in the domain. Okay, so that's where your mind should jump to, right? Because that's the one your enemy is going to pick. That's the one they're going to throw at you first. Try the hardest thing, okay? So that's how I want you to think about proving for all. When you're proving that there exists, it's kind of a bit easier. The weight is kind of off of your shoulders. It's your turn to fight back. So with a there exists, if you're proving that, you get to pick the value of the variable to try and make the predicate true. It's you who's throwing the punch at this point, okay? So to prove a there exists, p of x, you just got to find one person, one good value of the domain such that p of that value is true. Okay, you get to pick the best x in the domain. So you get to use your weapon, whatever you want. Your enemy doesn't get to do anything. It's their turn when the for all comes around. All right? So that's kind of how it's like a fight. Hopefully that makes a little bit of sense. That's the metaphor that's going on in my mind when I'm trying to prove these things. And weird things also happen when you have multiple quantifiers. You can have multiple quantifiers in a statement. That's totally fine. You can say, like, for all x, there exists a y such that for all z, there exists a p, blah, blah, blah. This can happen, and it's common. When you have a bunch of quantifiers to prove in your statement, you always have to work from left to right. Like, you got to do stuff for x first, do stuff for y second, do stuff for z third, do stuff for p fourth. Okay? It's going from left to right. So keep that in mind. And then think about the fight again. So if it's a for all, your enemy is going to pick the worst value, and then it's your turn maybe to counter it with a there exists. Then you move on. Okay? If it's a there exists, you pick the value, and you move on to the next quantifier. You're just trying to make the whole thing true, though. So really, you're thinking about every possible value for that x. Just one good one for the y, though. But it better counter the x, because that was picked first. Okay? Again, with examples, this will make more sense. But yeah, you might have a bunch of for alls, like some statement that has a for all x, for all y. And you might have a statement that's like, there exists an x, there exists a y, such that all this is true about them. The order of the variables don't really matter for those, right? Because it's like, it's your enemy's turn twice, it's your turn twice. The order doesn't really matter for those. You can swap them pretty easily. Here's an example. For all x, for all y, for all x and for all y, you can translate that to saying, like, for every x and y, either x plus y is less than or equal to x, or x plus y is greater than or equal to x. Okay? And that's a true statement. This is just saying, like, this is true for x and y, or this is true for x and y, okay? And it doesn't really matter in which order you pick the x and the y, right? It's gotta, these things involve both of them anyway. So the order doesn't really matter when you have a bunch of the same quantifier stacked right next to each other. This could have just as easily been, all right, pick the y first, then pick an x. Range over all of them, though. For every y and for every x, this is true for x and y. No real difference. So you can totally swap these things, not a big deal, and the whole thing is still the same. All right? When you have differing quantifiers, though, like you've got for all x, there exists a y, or there exists an x, such that for all y, the order always matters. Probably almost always, if not every time. Let me prove that to you, all right? With cats as an example, of course. So let's pretend here is our predicate. M of x and y, define that to be x sent a cat meme to y, all right? When you have a for all, or there exists, the same quantifier multiple times, the order does not matter. So in English, for all x, for all y, m of x, y just means, like, have the variables range over people, right? This is just saying that, all right, for every x and every y, x sent a cat meme to y. So this is saying that everyone sent a cat meme to everyone. And if you swap the x and the y, it still means that. There's no difference there, okay? Everyone sent a cat meme to everyone. That's where the for alls are coming into play, all right? Same with there exists. There's no real difference. You could swap these all day long. This is saying, all right, there exists an x such that there exists an x and there exists a y such that m of xy is true. So there's somebody, call them x, and there's somebody, call them y, such that x sent a cat meme to y. So if you want to translate that to better English, it would be someone sent a cat meme to someone. And again, you could have quantified over the y first. Doesn't matter. Okay, those could have swapped. It just means someone sent a cat meme to someone. Doesn't matter who comes first in this idea. Okay? But when you have differing quantifiers, the order really matters, and there's going to be a difference in what you're claiming and how you prove it. All right? So for example, if you have a for all first, for all x, there exists a y such that m of xy is true. Okay? That is saying that, all right, for all x is the sender, right, in this predicate. That's saying that everyone, because that's x, everybody, x gets to quantify over everyone in the universe, they all sent a cat meme. There exists a y. That's just one person, right? Everyone sent a cat meme to someone. You see that? Everyone, it could be a different someone each time. Everyone sent a cat meme to someone. For all x, there exists a y such that m of xy is true. All right? The flip side is different. There exists an x such that for all y, m of xy is true. So there exists an x. That's the first thing that happens, right? There's somebody that you were talking about, one person. Someone sent a cat meme to everyone. You see that? Y is being quantified over, and that's the receiver. So for every y, every person is getting a cat meme from this first person, this x person. Someone sent a cat meme to everyone. So yeah, do you see how these are two different statements? Okay, so the order really matters, especially when you're proving things. But just when you're trying to understand what the statement is talking about. All right? Everyone sent a cat meme to someone versus someone sent a cat meme to everyone. So please stare at this slide until it makes sense. Okay? So that's the idea. Here is a bit of a nicer example that involves real math. Okay? So let's define this predicate. P of x and y has got two things. Let's define it to mean, to be claiming that x times y is equal to 1. All right, so that's a predicate. It could be true or false, depending on the x and y, right? So for example, P of 1, 1 is true, because 1 times 1 is 1. P of 1/2 and 2 is true, right? Because you multiply them together, you get 1 again. So let's think about some of these, all right? So some of these are false, right? P of, I don't know, 2 and 3, totally false. Because 6 is not equal to 1, so that one's not true. But its negation is true, all right? So let's think about this. Is it true that for all x, there exists a y such that P of y? Is that a true statement, all right? So thinking about this in terms of these, let's figure it out. So your enemy first gets to pick x, right? Because that's for all quantified. So, and then it's your turn, right? And it's your turn because it's a there exists next. So this is going to quantify over every x. Your enemy's going to pick a horrible one, and then you have to counter it no matter which one they pick. You got to find some y such that x times y is equal to 1. So is it true that you can always do that, right? So your enemy gets to pick x first, and then you must counter it with a carefully chosen y. So for example, here's how the game might play out. So your enemy picks 1/2. Then it's your turn to pick. Can you find some y value such that this times the y is equal to 1? Sure, you can pick the 2. Do you see that? And pretend that the domain is positive numbers, so 0 is not possible here. P of, all right, let's say your enemy picks another horrible number. They give you 72/34. Yeah? And then it's your job to pick a y. You got to counter every possible x. Pick a y such that x times y can be 1 still. You can totally find it, right? 34/72. That's the one that counters that one. You can pick a different y for each x, right? That's the order, though. Your enemy gets to pick, then you get to counter it. And you try to make P of xy true. You can always find a value, right? You always just give the reciprocal, and this is a true statement, therefore. Does that make sense? You're going from left to right, your enemy's picking an x, you're picking a y, you're trying to make sure that P of xy is true. This is totally a true statement. So yes is the answer. Because you can always, no matter what value your enemy picks, for every value, you can always find its reciprocal and plug it in, and it works out. Okay? Let's try the flip side of that. Is it true that there exists an x such that for all y, p of xy is true? Again, remember, you're working left to right. You have to pick the x first, and then your enemy is going to pick horrible values to counter it with. All right? So you're forced to pick one x, and it better work for every y. Okay? You're saying something like, all right, my special value is 24. So you have to fix that. Fix x equal to 24, and then it better work for everybody. Like p of 24, your enemy might pick 2, p of 24, 3 better be true for every value. Like you have to put every value here. It has to work for them. And it's obvious that you cannot find any value such that that value times everything else is 1. That'll never work out. Okay? So this one's false. Does that make sense? You see how the order really matters there. And so an idea is that for all there exists is kind of easier in a certain sense than there exists for all, because like you have the home team advantage. You get to bat last. You get to counter the thing that your enemy picked, because you get to go second. It's harder to go first and pick something that works for no matter what your enemy can throw at you, because you have to try everybody. Okay? So hopefully these metaphors are somehow making a little bit of sense and sinking in. Again, this is a harder concept, these quantifiers. Okay, here's an example for you to try. Here's a predicate p. Its domain is every pair of integers. So x and y, they're both whole numbers. Could be negative though. So p of xy is the idea of x and y, adding them together and making 2. All right, so p of x and y, define that to be x plus y is equal to true. Or is equal to 2, sorry. So here are your 2 problems. Please try them, and then I'll come back and do them with you. Let me first just give you some examples of p. P of 1, 1, for example, is true. P of 0, 2, also true, right? Because x plus y is 2. P of like 2 and 2 is of course false, etc. All right. So is it true that there exists an x such that for all y, p of xy is true? And is it true that for all x, there exists a y such that p of xy is true? So try both of those. All right, so the first one, is it true that there exists some good x such that for every y, p of xy is true? So like, I don't know, maybe the value that you pick for x is 1. It better work for every value of y, right? P better be true for every value of y. Anything that your enemy could put here makes it 2 still. And of course, that's impossible, because you might pick your good value of 1, and your enemy might pick 42 and make it 43, and that's of course not 2. So that just doesn't ever work, right? And no matter what you pick, like you try every possible integer in the universe, like you can try 0, your enemy can again pick 42 and make it not 2, right? It's got to work for every y. You have to pick one x that works for every y that makes their addition 2. And that's impossible. So that's a no. Okay? Let's try the flip side, though. What was that one about? Is it true that for all x, there exists a y such that p of xy is true? Okay, so your enemy gets to pick a weird value, right? Like, maybe your enemy picks 0. Then you have to counter that. You have to find a good y such that p of xy is true, and it adds to 2. So, like, you can put 2 there. Is it true that your enemy picks something? Can you always find something to counter it next, because you go next, to make the answer 2? And the answer is totally yes, right? Because, like, here's x and y are supposed to add to 2. No matter what your enemy picks, right? They pick an x. You can just pick a y that is equal to 2 minus that x. And you'll always have an answer. Does that make sense? And it'll still be an integer, and so it'll all work out. Because of that order, like x then y, left to right, yes, it always works out. No matter what your enemy gives you, pick that y. That's your one good y that works for it. Okay? That's a true statement. Okay, moving on to logical reasoning now. So now that we can talk about predicates and we can speak logic kind of, we should be able to reason with it and like prove stuff, prove extra stuff, prove new things from old things. That's good to have, right? So let's talk about how we can get at that idea of proving things. So Usually when you're trying to prove something, you're like arguing that something's true, so the name for that is an argument. An argument is a sequence of propositions called hypotheses, hard for me to say. So you have all these hypotheses that you're assuming to be true, and then your argument is followed by some last proposition called the conclusion that you are claiming to be true from those hypotheses. Okay? So here's an example argument. It's like the first two things are your hypotheses. Some people put a line there. So these are two things. It's assuming these hypotheses. Assume P is true and assume P implies Q is true. And then it's claiming, this is the symbol that means therefore. It's saying that therefore Q is true based on those assumptions. Therefore. And this is a conclusion as well. Conclusion. Let me write that a little bit better. Okay. So it's saying, all right, assume this is true, assume this is true. It must follow then, I'm claiming, therefore, Q must be true. Okay, under those assumptions. So that's the idea. And we can talk about these arguments. We can prove them. So an argument we say is valid if the conclusion is true whenever the hypotheses are true. So like under the universes where this is true and this is true, maybe it's not true in real life, but assume that these two things are true there, and show that this is true. It must always be the case that Q is true. That's a valid argument. Under those assumptions, the conclusion is always true. Okay? Otherwise, we say it's an invalid argument. So secretly, it's like, all right, assume this, and they better lead to this. So secretly, every argument is just a bunch of the hypotheses anded together, and then an if-then statement. So like it's, if all of these hypotheses are true, then this conclusion is true. That's what an argument is saying, under those assumptions. So how do you assume that all of them are true? Just assume, well, if this one's true, and this one's true, and this one's true, all of them, then, right, that's what the implication means, then the conclusion is true. If all the H's are true, then the C must be true. That would be a valid argument. All right, so the process of showing that an argument is valid, that's what it means to be a proof. Okay? So there's secretly an implication going on under the hood. All right, so that's all a proof is. Under these hypotheses, show that this conclusion always is true. If that's valid, you have proven your statement. That's a proof. So the easiest way to prove something is to use a truth table, at least for us right now. That's the easiest way to do things because we're comfortable with those probably by now. So here is an argument. So assume these two things above the line are true. So assume that it's not true that P implies Q, and assume that Q implies P, and show that it's always the case that not Q is true no matter what, under those assumptions. Okay? So here's how you can do that using a truth table. So let's try all the possibilities for P and Q. Whee! You got your true, 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 false, false, true, false, false. And then we have all these other things. So what happens when not P implies Q? So P implies Q, right, is just normal P implies Q is, if you go back to the truth table, it's going to be, this is just normal P implies Q. It would have been true, false, true, true, right? But we're negating that. So it's false, true, false, false. All right? And then we're assuming that Q implies P is true as well. And that is true everywhere except true implies false. Right? That's the one place that is false. So it's true everywhere else. True, true, true. That's how you make the truth table. And then we also have the conclusion, not Q. Right? So that is false, true, false, true. And so now let me show you how to use this truth table to prove the statement. So again, it's assuming this is true, and assuming this is true, show that this is always true. So we only have pieces of the truth table that we care about, actually. So under the assumption that this is true, well, there's only one time that this is true, right? That case. So assume that we're in this row only, right? Assume that this is true, and assume that this is true. Q implies P. So assume that under these assumptions, there's only one row of the truth table where they're both true, right? Show that not Q is true. And it sure is. You see I'm reading the truth table? I only care about the row where both of these are true, because that's what we're assuming. Assume that both of these are true. Show that it's always the case that not Q is also true. That's our conclusion. So under the assumption that those two things are true, we can always show that the conclusion is true as well. And that's a proof. It has been proven. Not Q is true under those assumptions. Okay? It's not always the case that not Q is true, but only in the cases that we cared about is it true. Okay? Under those assumptions is it true. So that's what it means to be a proof. Showing that an argument is valid. It's a valid argument. If this is true and this is true, then this is also true. I hope that makes a little bit of sense. You try it now. Prove that this argument is valid. I'll do the truth table again for you, assuming you've tried it yourself. True, 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 false, false, true, false, false. We have P if and only if Q, and that's true when their values correspond, right? When they agree. And so that's a true, a false, a true. And then we have P or Q. That's true if any of them are ever true. It's only false here when they're both false. So it's true all these places. And then we were trying to show, like, P, right? P is the conclusion. So P, I mean, it's already over here. I'll just write it again. Why not? True, true, false, false. So again, these are the hypotheses. So under the assumption that those are both true, where are the rows where those are both true? It looks like it's, well, here's where this one's true, but this one's false there, so that doesn't count. And here's where P or Q is also true. So this is the only row that matters. And we have to show that when those are both true, assuming those are both true, it's always the case that P is true. And what do you know? Sure is. And so that's our conclusion. That is us showing that the argument is valid. Under those assumptions, yes, it's always the case that P is true. And so that is a proof. We've proven this. Valid. It works out. Checks out. All right? Writing out truth tables, especially for very large formulas or things that have quantifiers in them that like have infinite things that you need to talk about. You can't really build a truth table once things get large, so we need a different way to prove things. And so we have some rules, just like we had some laws for how to simplify our propositions. We're going to have some similar rules for proving propositions. They're called rules of inference, all right? Because nobody wants to use truth tables all day long. So we'll find some patterns again, and we'll write them down so that we can use them. Right? These are called rules of inference. And there's a table in your book. It looks like this. It's like, if you have these things, you can conclude this. If you have these things, you can conclude this. And so some people wrote down some important ones. They give them names, and we're going to use that. All right. So there's a rule called modus ponens, and that's Latin. And let's prove that using a truth table so we can use it forever. Right. Modus ponens stands for, it's the Latin for mode that affirms. So it's saying if you have P, so assume this, right? If we have P and we have P implies Q, if those are true, assume those are true. If we have these things, if we have this, then we know that Q is always true. We know this is true. So that's like another tool in our box now. We can write down Q if we have these things. We know it must be true. We know this is true. And that might help us achieve our normal, our goal that we have in our real proof that we're trying to prove. All right? So if we have these things, then this is true. If you have P and you have P implies Q, then you also have Q. There's a flip side called modus tollens that involves negations, and we'll get to that eventually as well. But let's prove that modus ponens is always true. So here's modus ponens. If you have P, if you know that P is true, and you know that P implies Q is true, which is right, if P is true, then Q is true, that's how you can pronounce it sometimes, then we know that Q is always true, therefore Q. Now let's prove this using a truth table. P, Q, P implies Q, and then Q is the conclusion. I'll just write it again over there. So true, 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 false, false, true, false, false. Alright, so P implies Q, that's true, false, true, true, and then Q, I'll just write it again, true, false, true, false. So, under the assumption that P is true, and P implies Q is true, so here are the places where P is true, here are the places where P implies Q is true, and so we only take it when they're both true, which means we're only talking about this row, right? This is the only place where P is true and P implies Q is true. We need to show that Q is also always true. And yeah, it is. So we can always conclude that. If you know that P is true and P implies Q is true, you also have in your arsenal that Q is true. You can write that down too. You know that's always true. So that's a proof. All right. So now we can write that down and use it forever, no matter what P and P implies Q are. Whatever P and Q are, fill them in from your proof. You can use modus ponens to get out a Q. All right. And the rest of these are similar. You can prove them. Let's use them. So maybe you're going to want to pause this. You're going to want to go flip back and forth between these in this example if you want to try it yourself. But let's use these rules of inference and the laws of logic as well. We'll need those too, maybe to break things down. Let's use those to prove that this argument is valid. Right? It's a true statement. That's a proof. So assume P implies Q and Q implies R, and assume not R is true, so R is false, and then show that it must be the case that not P is true. Okay? And so we can eventually end up using all these things. Let me show you how you can do this proof. We're going to use these inference rules to prove that the argument is valid. We also want to name each rule that we use. Like we're going to start somewhere and we're going to end up at not P. Okay? But we get to use these. We know that they're true. We're assuming that all these three things are true first, though. All right? So you just kind of stare at this and you're like, all right, I need to do all this. So modus ponens is like, if you have this, like you can go forward. Like you have the P, you can go forward to Q. Right? Modus tollens, if you look at it long enough, it's like you have this and you have not Q, you can kind of go backwards to not P. And if you stare at that long enough, it's kind of what we need, right? Because we have Q implies R and not R, so we can go backwards to not Q. And then we can do that again. We have not Q, we can go backwards to not P with a bunch of applications of modus tollens. You see that? That's the idea. That's kind of how we're going to do it. And there's different ways, actually. And we can talk about that too. But here is a proof of that, right? So these three things we know. We are assuming them. So, like, here's part one of our proof. We have Q implies R, right? We have that by assumption, we'll say. That's a hypothesis. We have that for free. So that is true by assumption. And remember, our goal is to use these things to prove that not P is true, right? So we have that by assumption, and I want to use modus tollens, right? So I also need the negation of that conclusion, which is not R, and I have it there. So that's also something that I have, not R, by assumption. And now, you'll also see why I'm numbering these. And now I can get, right, from these two, I can get not Q with modus tollens, right? Because that's something that I can prove. See that? I went backwards from here to here to get with that involved, right? So just plug in. It's weird because Q exists here, but this is Q, this is P in the modus tollens rule. Does that make sense? And so we get it back, the negation of the hypothesis, not P. That's using modus tollens with these two things. I need those two things to apply it, and I had them. So this is by modus tollens on 1 and 2. That's why I numbered these. So I'm saying this is how I'm using modus tollens on those two things. So now I have not Q. And I can use this and this to get not P. You see that? So in order to use modus tollens, this can be my 3. I need P implies Q, and I have that by assumption. That was one of my hypotheses. By assumption, and then I can apply this and this with modus tollens again, just look at the table, to get not P. Modus tollens Let me write that slightly better. On, I guess, 4 and 3, right? And if we're doing it in order, like I guess the negation needs to come first anyway, so I guess it could have been 3 and 4. No big deal. And that's what we wanted, right? We've just shown that from these assumptions and these rules of inference, we can end up with our conclusion, and we know that this is true given the fact that all of these rules are valid to apply. So that means the whole thing is valid. That means the proof goes through. Check. Isn't that cool? So we just proved this. Assume these things are true. We just proved that not P is true under those assumptions, and that's a proof. Those are our first example proofs, so that's exciting. So that's where I want to stop for today. We'll come back next time, and I'll give you some more examples. Okay, I'll start it off with a question for you. So I'll see you there.